Assalamualaikum, brothers and sisters.
Waalaikumsalam.
Waalaikumsalam, sir.
Yeah, we should start. Shall we? I will start.
Yes, sir.
Okay. Again, Assalamualaikum warahmatullahi wabarakatuh. Let's start our day with the recitation of Ummul Kitab Al-Fatihah. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahil alamin. Arrahmanir rahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Okay. Today we have Ustaz Azamuddin to lead a dua for us. I think Ustaz is ready now.
Yes, sir.
Tafadhal
Can-
Ustaz.
Okay, can I start?
Tafadhal Ustaz.
A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Allahumma alhimna ilman na'rifu bihi awamiraka wa na'rifu bihi nawahiyaka warzuqna. Allahumma balaghata fahmin nabiyyin wa fasahata hifzil mursalin wa sur'ata ilhamil malaikatil muqarrabin wa karimna Allahumma binuril ilmi wa sur'atil fahmi wa khrijna min zulumatil wahmi waftah lana abwaba rahmatika wa 'allimna israra hikmatika ya rabbal alamin.
Shukran Ustaz. Okay. Let's look back. We are still on linear programming. What did we do last class? We have two items, right? Let's say we have two items. We want to make some decision. Let's say we have a graph, horizontal axis, x1, and then we can graph it x2. It's easier to graph on a piece of paper, two-dimensional. Let's imagine, like in our exercise, we have what? Mimi diamond, a bracelet, and necklace, two items. Let's say if you are running a jewelry store, maybe not only bracelet, not only bracelet and the other one, what was it? Say we have another item, ring, pendant, for example. We have more than two. Then let's say we have another dimensions, x3. And then another dimensions, x4. And some more, x5. And all this line is running in space in different directions. Can we just figure out something like that? We have so many items to look at it. Then something like this, so many lines. How are we going to find the feasible region, in this case, feasible volume, let's say? And then we want to find the corner point. There's no corner point. We have aspects here. Some aspects somewhere here, aspects here, and many corners to do. So how do we do? Can you graph this?
Hard to graph, sir.
Cannot, right? Cannot graph. So we have to use impossible. So we have to use what we call it simplex method. We are going to use what we call it simplex method. Well, it sounds simplex. It's, hopefully it's simple. Let's go through. Just now in last two classes, we were working on two dimensions. That means two variables, and we have maybe 2 or 3 constraints. Then it's okay for you to do manually. Let's imagine this is a case of delta L lines. No need to read the rest. Read at the bottom there, the yellow color, 60,000 variables. And then 40,000 constraints. So this data line has used linear programming with 60,000 variables, 40,000 constraints. And by doing that approach, the company claimed they save 300 million a year. Okay, let's have a go. For purpose of illustration, there's a reason later on. I will use two variables for purpose of illustration in simplex method. I will illustrate using two variables so that I can show you how it moves from point to point in two dimensions. Let's look into this example. Elite Furniture Company produce chairs and tables. The manager of the company has estimated that each chair requires 3 hours of carpentry and 2 hours of painting. On the other hand, each table requires 3 hours of carpentry and 4 hours of painting. Then for the coming production period, the company has allocated 120 carpentry hours and 100 painting hours. The company can make a net profit of $7 or 7 ringgit for the chair and then 10 ringgit for the table. Then within the limited constraints or resource constraints, how many chairs and how many tables the company can produce so that you can maximize the profit. Okay, we are not going through the graphical in detail like last two classes. Let's say we solve this using simplex graphical method. We summarize the element here, chairs and table. Let's say chair, number of chair x1, number of table x2. Then each of these have to go through two processes, carpentry and painting. And then they have given here 120 hours, 100 hours, and then the profit 7 and 10. Let's say you formulate this problem and solve graphically, and I think this is the formulations. You want to flashback the formulation using these informations. 7, 10 profit, 7, 10, 7 and 10 carpentry, 3, 3, 3 for x1, 3 for x2, given 120 hours. 3, 3 given 120 hours, we can use less or equal to or up to 120, not more than this one. The second constraint, 2 for 100. 2 for 100. And then of course the non-negativity constraint. If we were to solve this graphically, I think this is the graphical solution. This is the feasible area. Let's say we use ISO profit line. We can get this ISO profit line after we move up and down, and we touch this extreme point, and this reflect to 30 x1, 30 chairs, and 10 tables. So the solution using the graphical method, 30 chairs, 10 tables, x1, x2, and the profit, if you substitute this into this objective function, you get 310. Okay, let's use this for our illustration in simplex. So in simplex, okay, simplex, similar, we are trying to solve a few equations. So it is a method, simplex method is an algebraic procedure for finding the best solution to the system of equations, set of equations, namely set of the constraint equations. Constraint equations form a system of simultaneous equation with the variables. And then the next step, after we do the formulation is to be rewritten, or we call it transformed, into a format called standard form. Again, constraints are written as equations with non-negative right-hand side value. On the right-hand side value cannot be negative. Variables are items, and of course variables cannot be negative, but the coefficient can be negative. The variable itself, like table, cannot be negative, chair cannot be negative. Then the purpose, still the same, objective function is either maximization or minimization. So similar to graphical method. Okay, let's figure out you have 1 million ringgit. Let's say you have 1 million, and this 1 million you are being given 1 million. Then you have the discretion whether you want to invest all the 1 million or keep all the 1 million, invest all, or you don't keep any at all, or invest part of it, or keep part of it, or keep all in your drawer and you don't invest at all. So in this situation, you are given resources of 1 million. So in other words, we can say you can invest anything less or equal to 1 million. Of course, you cannot invest more than 1 million. Then if you invest 1 million with 10% return, how much you get at the end of the year? 10% return of 1 million. Say you invest all you invest, you get 100,000. Agree?
Agree.
Agree. So let's say you invest part of it. So you invest only 800,000, and then assuming with 10% return, and then the balance, let's say you cannot invest for certain reason, and you have to keep in your bag or in your drawer or in your under your pillow. So how much dividend you get out of 800,000?
80K.
80,000, 80K. How about the 200,000 in your drawer? Does it generate anything?
No.
No, you get 0. Okay. Then you keep all the 1 million in your drawer. So you invest nothing. What do you get? Nothing, right? So you keep all. That means this 1 million is doing nothing. You have the 1 million resources, but you don't make use of it. It generates nothing, 0 return. So in a commercial environment or in business environment, those resources like this money, you keep somewhere and you don't generate anything, we refer this as slack resources. Or if we don't have the opportunity to use it, we refer this as slack resources. Let's say we refer this slack as S. Let's write this in some form of equation. So let's say we have a cash, the resources it is made available to you 1 million. So you can invest up to 1 million. Anything less than 1 million. So let's write into our equation. Let's say I is investment. S is the amount you don't invest. If I were to write this one, I is less or equal to 1 million. Now I want to change this less or equal to, I want to make it into equal sign. So if I were to invest, say 800,000, what is the amount not invested here in this
200.
200. If I were to invest 500,000, the amount not invested is 500. If I were to invest 500, what is the amount not invested? The slack in here,
500.
500. Okay, let's rewrite this. Now you want to change this into equal, because now the 200, the 500, you cannot see. If I were to write in this way, investment plus slack equal 1 million. That means if I were to invest 1 million, what's the value of slack?
0.
0. If I were to invest 800,000, what's the value of slack?
200,000.
It will, 200,000. It will sum up to still 1 million. Okay. So again, I plus S is to 1 million. So if we invest 1 million, and then with 10% return, you get 100,000. Again, if you keep all of them, slack is 1 million, you get nothing, dividend 0. Okay, now in Simplex, let's go to Simplex. In Simplex method, the resource constraints, we are going to change this inequality sign, convert the inequality symbol here into equality, into equal sign, by introducing slack variables S. And then the equation that we have just now, this one, the constraint equation, 3x plus 3x2 initially was less or equal to 120. It will become, oh, where am I? So 3x1 plus 3x2 plus S1 equals 120. Let's say S1 refers slack for the first constraint. And then the same thing here, 2x1 plus 4x2 less or equals to 100. Can 2x1 plus 4x2 plus S2. S2 represents slack for equation 2 equal 100. So this is the one we have. Now, if I do nothing, this 120 is 120 carpentry hours allocated for you. You are given in the production floor 120 hours for carpentry, and then painting 100 hours. Let's say I decide not to produce any chair, any table. What's the value of X1?
0.
0. X2?
0.
0 also. Then S1?
120.
120. That means the carpentry hours is not used at all. The same thing, if I were to do nothing, then the painting hours is 100, not used at all. Okay. Now, the next thing is, in Simplex method, all variables must appear in every equations. So we had to do some trick. Those not relevant to the equation, we had to put the variables in, but this time we cheat a little bit. Tomorrow Ramadan cannot cheat. Now cheat a little bit, not cheat in the literal sense. So mathematical trick, by assigning 0 coefficient to other not relevant slack variable to that equations. So what we have is something like this. We have 4 variables, x1, x2, s1, s2. Since it says all variables must appear in every equations, so we have to put s2 here. We have to put s1 on the second equation, s2 on the first equations. So we have 4 variables reflected in every equations. So now we assign 0 coefficient, 0 S1, 0 S2. Don't ask me why. This is the procedure for Simplex. And then when the same thing on the objective function, we also introduce S1 and S2 at the objective function by introducing 0, 0 coefficient and 0 coefficients. So this whole set of equation, after you introduce S1, S2, after you change this less equal to into equal sign, less or equal into equal sign, after introducing these slack variables, we call it standard form. Take note, standard form. And then, okay, let's look back. How many equations do we have here? How many equations? 1, 2. Two equations. Two equations. How many variables? 1, 2, 3, 4. 4 variables. 2 equations, 4 variables. Can you solve this simultaneously? Cannot. I thought there's some expert who say can. Okay, let's say we cannot solve this. Now we have to do something. In here we have the number of variables are the decision variables. The number of equation are the number of constraints. In our case, we have 2 equations, 4 variables. 2 equations, 4 variables. 2 equations, 4 variables. Okay, next. Then the next step is we are going to find what we call basic solution. A basic solution can be either feasible or not feasible or infeasible. The next rule is a basic feasible solution is a basic solution that satisfies non-negativity conditions. So what we do is we assign, just now we have 4 variables to equations. So we assign 0 to 2 of the 4 variables. If we assign 0 to 2 of the variables, the variables that we make it equal to 0, we call it non-basic variable. And then the remaining variables that we did not make it equal to 0 is referred to as basic variable. Okay, what is it? What it says here, if we do nothing, x1 equals 0, equals 0. That means the idea is you want to solve these equations. You want to solve these equations. Okay. We have 4 variables. Okay, again, 4 variables to equation. We cannot solve this. So, in order to solve this, we make any 2 of these equal 0. Okay, any 2 of these. Let's look at it. Let's say we are going to do something. So now, how many variables we are going to make it equal to 0? To determine a basic solution, set n minus m of the variables equals 0. What is n? What is m? So m is number of equations, n is number of variables. We have more variables than number of equations. So we are going to make this n minus m number of variables equal to 0. Again, I repeat, the n minus m variables being set equal to 0, we refer as non-basic variable. I will repeat this word over and over. The remaining m variables that we didn't set to 0 is referred as basic variable. Take note, non-basic variable, basic variable. Okay. In this case, let's say we start at the origin. Let's say we start at the origin. When we start at the origin, x1 equal 0. x2
0.
equal, and then x2 also 0. Since we let's
0.
say we start at the origin in the graph, x1 equals 0, x2 0. This one also 0. So s1 equal S1
120.
120. The same thing here. If x1 is 0, x2 is 0, then of course here 0. S2 equals 100.
100.
100. So this is what we get. Obtain a basic solution to make equal number of variables and equation by assigning two variables equal to 0. In this case 2. Let's say we start at the origin. So we make x1 equal to 0. And we also make x2 equal to 0. And we get S1 equal to 120, S2 120. S1 represent the carpentry hours. S2 represent the, S1 represent the carpentry hours not used. S2 also represent the painting hours not used. It makes sense, right? We do nothing. Since we do nothing, we are producing nothing. The allocated number of hours for the carpentry not used. The number of hours allocated for painting also not used. Okay. Now, we are going to find what we call basic solution. In this case, the basic solution is x1 0, x2 0, s1 120, s2 100. So in linear programming solution, every variable must be greater than 0. We cannot have any of this negative. We cannot have any of this. So the basic solution is a feasible solution. In this case, if we get all positive, we refer this as basic feasible solution. Okay, what does it mean? If you look back at the graph, x1 is 0 as is at this point. Agree? Is at this point. x1 is 0, x2 is 0. It is within this feasible region, right? It is within this feasible region. So we get a basic feasible solution. Somewhere here, feasible, feasible, feasible. So x1, x2 is 0, we get basic feasible solution. Okay, let's move on to this statement. If, let's say we put any two of the variables, in this case, let's say x1 equal to 0, s1 equal to 0. Then we get, if we solve, we get x2 equal to 40, s2 we get negative 40. So in this case, the basic solution is not feasible, is infeasible. Okay, take note, x2 is 40. Okay, x2 is 40. Let's look at the graph. x2 is 40, somewhere here. Is it within the feasible region? x2 is 40? No. So we are not getting a basic feasible region solutions. So in Simplex, what we are trying to do, we are going to test any of this point, such that we always get, wherever we test, we are within the feasible region. You are within the basic feasible solutions. Basic feasible solution. Whether optimal or not, we are going to work on later. So this is the concept of trying to get basic feasible solution, and we may get basic solution is also not feasible. But our approach, we are trying to find basic feasible solutions. So in most cases, we start at the origin. That means x1 is 0, x2 is 0. Okay, let's move on. The next step, we are going to set up what we call it Simplex tableau. So we are going to translate just now the standard form, the content of the standard form into the Simplex tableau. So the purpose is to find the initial basic feasible solution. The initial feasible solution. We are not trying to find optimal. Initial basic feasible solution anywhere within the feasible region. So there are 3 steps. The first step in Simplex, the same thing, formulate the problem. We call it develop the linear programming model, and then convert it into standard form, or we can say construct the standard form. Standard form means after you put the slash subtract after changing the equality sign into equal sign. Then set up the tableau form. I don't know how to pronounce this, tableau or tableau. Let's pronounce tableau form. So this is the tableau form. Just a table. Looking at it, it looks like just a table. On the left-hand side here, the first column, we refer this as basis column. And then on the right-hand side, here, we have the solution column represented by B1, B2, B3, B4, up to whatever number. And then at the top, here are the variables, X1, X2, X3, X4, X5, X 60,000. So at the top are the variables. And then we have the coefficients of the objective function written here. We call it C row, C1, C2, C3, C4, C5, and until Cn. And then somewhere inside here, this one A, we call it A matrix. This represents the coefficient of the constraint equations. A1, A11, A row 1, column 1, A row 1, column 2, A row 1, column n, A row number 2, column 1, A row number 2, column 2, A row. So this will be the coefficient of the constraint equations. Okay, so I call this C row. So we refer as A matrix. Then the solution column, and then the basis column. Yeah. Okay. Now it doesn't make any much sense to you yet. You will take note of this. You are going to play with this. Now, to do simplex method, there are several steps. Now, determine the entering variable by finding out the most positive net evaluation index, Cj minus Zj, the corresponding column called pivot column. This is after we set up the initial tableau. Okay, you don't have to memorize this. Just take note of the word entering variable, net evaluation index, pivot column. Then after that, we are going to determine leaving variable. Then we are going to calculate ratio. We are going to determine what we call it pivot row. Then we are going to find pivot element or pivot number. So we are going to determine the leaving variable by selecting the minimum ratio. The corresponding row is called pivot row. The element at the intersection of the pivot column and pivot row is called pivot element or pivot number. The next one, we are going to find the new value of the pivot row. We are going to calculate the new coefficient of the pivot row by dividing the elements by the old row in the old row by the pivot number or pivot element. Okay, next step, calculate the new values of other row in the new table. That means we call this elementary row operations. And then we are going to determine whether our solution is optimal or not by checking the Cj minus Zj values. We refer this as net evaluation index. If all these values are negative or 0, then we find we already achieved the optimal solution. That means the solution is optimal. If not, we repeat the process. All right, let's have a go. Okay, this is the initial tableau that we have set. Take note, on the left hand side, basis column. On the right hand side, solution column. At the top, x1, x2, s1, s2. Okay, let's look back at our equation, at our standard form. x1, x2, s1, s2. We have 4 set of variables. x1, x2, s1, s2. Then we have C row. These are C row. These are this 7, 10, 0, 0 is the coefficient of the objective function. Okay, let's flash back. We are writing this 7, 10, 0, 0 at the top. Okay, let's see. 7, 10, 0, 0. Let's refer this as coefficient Cj. C column 1, C column 2, C column number 3, C column number 4. And then we write the A matrix. These are the coefficient of the constraint down here, the coefficient of the constraint. Okay, let's look at this 3, 3, 1, 0, 120. This is the coefficient of the constraint 3, 3, 1, 0, 120. 120 is the right-hand side value we write in the solution column. This 120 is written at the solution column. This 0, 1, 3, 3 or 3, 3, 1, 0 is written in the A matrix. Okay, take note. 3, 3, 1, 0. The 120 is written at the solution column. Okay, let's look at the second row. 2, 4, 0, 1, 100. Now 2, 4, 0, 1, 100. Okay. So we just put in this one. Now, if I were to start at the origin, what's the value of x1?
0,
0. x2?
0,
0. That means x1 become basic or non-basic variable. Anything we make it equal to 0? Non-basic. Non-basic. x2 basic or non-basic? At the origin. Huh? Is that all?
Non-basic.
Non-basic. S1 basic or non-basic?
Basic.
Basic, because we didn't make it into 0. S2
Basic.
basic. Okay. Now we have set up. This is again, I repeat, at the top here, the coefficient of the object functions, and then inside here, the coefficient of the constraint, and then on the right hand side here is the solution column, the solution. Now in Simplex, we are going to bring the basic variable. We are going to bring the basic variable into the basis. We are going to bring the basic variable into the basis. That means we want to bring the basic variable that belong to this constraint into the basis. Okay, I repeat. X1, basic, non-basic, one more time.
Non-basic.
Non-basic. X2,
Non-basic.
None.
non-basic. S1,
Basic.
basic. Okay. S2,
Basic.
basic. So we are going to bring the basic variable into this, into the basis. We call it bring the basic variable into the basis, something that belongs to this equation. Which one belongs to this equation? S1 or S2? The basic variable.
One.
S1. So we bring the basic variable S1 into this basis column. Something. Then we also want to bring the basic variable for equation 2, the constraint number 2. Which one should I bring here into the basis column? S2. Good.
S2.
S2. The next step is we want to determine the coefficient here. The coefficient is picked up from here, from this 0. Then we are going to bring down here.
0.
So we take S1, the
0
coefficient
and
is
0.
0, 0, and 0. Okay, done with the initial tableau. So this is the constraint coefficients or marginal rate of substitutions. This number here, we call it unit column or unit vector. Okay, what does it mean? From here, S1, where's the solution? Can you look at the solution? S1 equal to what number? What's the value of S1? Look at the solution column. S1 equal to
120.
120. S2 equal
100.
100. Is it logical? We say X1 non-basic, right? Non-basic equal 0. X2 also non-basic equal 0. Anything not in the basis column become non-basic variable. Anything on the basis, any variable on the basis column, we refer this as basic variable. Does it make sense? If X1 0, X2 0, we do nothing, right? We produce nothing. So that means your carpentry hours unused, 120. Your painting hours, S2, unused, 100 hours, not used. Okay, is it the best solution? I don't know. So now, what does it say here? The same thing. Look back at the graph. If we look at the graph, we are actually at this point. X1 is 0, X2 is 0. If X1 is 0, X2 is 0, what is your profit? Z.
0.
0. Straightforward. So we are at this coordinate. So solution at point O, x1 0, x, it makes sense. X1 is 0. We do nothing. Of course, your profit is nothing. Now, let's find out whether this is a best solution or not the best solution. So what we are going to do, this is the same set. We are now going to find the zj value. Zj value, what's zj? Z value, actually this is the marginal profit, we call it here, marginal profit inside here, is the sum of Cj times Aij down here, plus this one, plus this one. So Z for X1, for column 1, 0 times 3 plus 0 times 2. What do you get? 0 times 3 plus 0 times 2.
0.
0. So 0 times 3 plus 0 times 2 is 0. This is the thing. 0 times 3. Yeah, we get 0. How about the second one? The second row, ZJ, row number, column number 2.
0.
0. Column number 3.
0.
Column number 4.
0.
0.
Solution.
0.
0. 0. Okay, what is this 0? Why I put bold? This is the solution. That means the value of Z, here, the solution is 0. Why 0? Because x1 is
0.
X1 0.
x2
0.
0. But is this the best solution? You produce nothing. Is it the best solution?
No.
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 No. Let's find out whether we can improve from here or not. So to improve from here, we are going to find what we call it Cj minus Zj. 7 minus 0. Okay, Cj minus Zj. Okay, here the value of object function is 0. Cj minus Zj. We refer this as net evaluation row. Net evaluation row. We are going to find what we call it net evaluation index. 7. What is it? Cj minus Zj. 7 minus what number?
7.
0. 7 minus 0, we get 7.
7.
7.
10.
10. The same thing. Here, 0 minus 0. 0. 0 minus 0. 0. Okay. You watch out carefully. This is exciting. The next thing is we look at the net evaluation row, net evaluation index. We see 7, 10, 0, 0. What it says here, you look into this 10 equal this 10. This 7 equals 7. If we are trying to improve our next, I call it next iterations, that means next tableau. This is the first, we are still at the initial tableau. We have not moved on yet. If we are going to improve in the next round, we have to choose the highest value in order to improve the solution. I mean, it will be faster if we choose the higher value than the lower value. So what we do is we look at the net evaluation index, or I call it the net evaluation row, or sometimes I will say Cj minus Zj. Choose the highest number. What's the highest number along this one?
10.
10. Then 10, let's mark this 10. I mark 10, or you want to shade when we work, you want to highlight, up to you. Let's mark with this arrow. This column represent what we call it pivot column. So after we mark this one, we get this column. We refer it as pivot column. This pivot column corresponds to which variable?
X2.
X2. This X2, we refer this as entering variable. Enter what? Where to enter? It will enter this basis column. X2 will enter the basis column. But how? This is occupied. So one of these has to leave, have to vacate this apartment, this basis. One of these has to vacate. So how to determine which one have to go? Then we calculate what we call it the ratio. We are going to determine which of these S1 or S2 have to go. So let's find the ratio. How to calculate ratio? Solution divided by pivot column coefficient. I repeat, solution divided by pivot column coefficient. Solution divided by pivot column coefficient. And we do the same for the second one. 100 divided by 4. Solution divided by pivot column coefficient. 100 divided by 4. 100 divided by 4 is 25. 120 divided by 3, 40. Now, the next step is we find the lowest ratio. Which one is the lowest ratio in here?
25.
25.
25 represent the lowest value. So we mark this lowest value. Then we refer this as pivot row. We get what you call it pivot row. Pivot column, pivot row. There is another word, pivot element. The number at the intersection of the pivot column and the pivot row, we refer this as pivot number or pivot element. Oh, sorry. So again, just now we determine the ratio for what? We want to determine who leave the basis column. So the leaving variable will be S2. S2 will leave, X2 will enter in the next round. And I repeat, the number at the intersection of the pivot column and pivot row, we call it pivot number. So what is the pivot number or pivot element? 4. Okay, after this we have a game, how to play with this number 4. The next thing is, the next round, we are going to determine a new pivot row coefficient. The next one, we are going to calculate this new pivot row coefficient, and we are going to calculate again this old, I call it this row coefficient. We are going to calculate again. So now what we are going to do, we are going to make it into 1. And this number, in next one, we call it unit column. You will make it into 1, and then this one becomes 0, 0. Like here, unit, this is unit column, unit column. So we are going to make this into unit column. To make it unit column, to make it equal 1, how do you do? Divide by the same number,
Divide
right?
by 4.
Divide by 4. So we divide by 4. By all this, we are going to divide by 4. 2 divided by 4, 4 divided by 4, 0 divided by 4, 1 divided by 4, 100 divided by 4. Okay, let's move. So this is now the second iterations. Notice now, just now x2 was entering variable. Now enter the basis. S1 stay, S2 leave already. Bye-bye. When X1, sorry, X2 come in, what's the coefficient of X2 from somewhere here?
10.
10. So we bring 10 here. It's no longer 0. It was 0 because just now was S2. So this one, this time 10. Then we are going to recalculate this one. We call it the new pivot row divided by 4. So 2 divided by 4. I leave it in fraction. So become, so here 1. Here. The idea is to make it unique column. Okay. Now, okay, 1, half, 0, 1/4, 25. And this row, let's say I refer this as old row. I cannot use this anymore for the new one, so I have to remove this one. So take note of this one. We are going to use this. I refer this now old row coefficient, and this is the new pivot row coefficient. Let's calculate this one. Now we cannot use this anymore. Let's calculate. This is the way to calculate the new row coefficients. X1, X2, S1, S2 solution. This was the old row, 3, 3, 1, 0. Okay, let's 3, 3, 1, 0, 120. 3, 3, 1, 0, 120. The old number. 3, 3, 1, 0, 120. And then the new pivot row, the number we just computed just now, half, 1, 0, 1/4, 25. Where do we get it from? Here. Half, 1, 0, 1/4, 25. Now we want to replace this number. So I call the new one, we call it new row coefficient. So we try to find what we call it new row coefficient. I lay down this way, calculate the new row coefficient, S1, X2, S1, S2 solution, and our pivot column was here. Take note of the pivot column was here. To calculate the new row, the old row coefficient minus old row pivot column coefficient, this one, times new pivot row coefficients. So in this case, old row coefficient 3 minus old row pivot column coefficients times new pivot row coefficients, I get this number. Someone want to check? 3 minus 3/2. Is it the same? Do you get 3/2? 3?
Yes.
Yes. Because 3/2 minus half over 2, 3 becomes 6. 3/2, 3 minus 3. Okay, the same thing on the next one. We try to get the pivot, the new coefficient. Old row coefficient was 3 minus old row pivot column coefficient was also 3 times 1. 3 times minus 3 times 1. You get 0. Same thing for here. 1 minus 3 times 0, 1. 0 minus 3 times 1/4. You get negative 3/4. Then here 120 minus 3 times 25. 120 minus 75, we get 45. Are we following? So we are going to replace this number. Take note, 3/2, 0, 1, negative 3/4, 3/4, 45, somewhere here. We are going to replace this number. Okay, I look back again. 3/2, 0, 1, negative 3/4, 45. Okay, let's replace 3/2, 0, is it right? 3/2, 0, 1, negative 3/4, negative 1, negative 3/4. What's on the right hand side? 45.
45.
45. So we change this 45. So this is the new set, the second one, the second tableau. Now we want to find the solutions. Let's say find Z. How to find Z? 0 times 3/2 plus 10 times half. Because this 0 times 3/2 because 0. 10 times half is
5.
half, 5. Here, because here 0, 10 times
10.
10. Oh, I forgot to mention. Remember, I did mention we want to convert this. Just now, the original pivot column was somewhere here. We are converting this into unit column, 1, 0. That means if you have more than 2 columns, one, the gang, I mean, anywhere up or down must be 0. Okay, let's proceed. Z for S1.
3/2.
1 times 0 plus 10
Oh,
times
sorry,
0.
0.
0.
0.
0. You don't say anything. 0 times 3, negative 3/4 plus 10 times 1/4.
5/2.
5/2. 0 times 45 plus 10 times 25.
250.
250. Okay, what does it say here? Where's the value of x1 in here?
5.
X1, basic or non-basic?
Basic.
One more time. Is it in the basis column, x1?
Oh, sorry. Non-basic.
Non-basic, non-basic. If non-basic equal what? Equal 0. X2, what's the value of x2? Now basic or non-basic, x2?
Basic.
Basic. How do you know basic?
Is in the basis column.
Is it in the basis column? So now look into the solution. You get the value. What's the value of x2?
25.
25. Where's S1?
45.
45. Look, the number reduced. Now it is reduced from how many hours to 45 hours left because some of the carpentry hours have been used up to produce 25 units of tables. X2 represent tables. So this 25 represent the number of X2. So S2, 45. Where's the value of the profit now? Z.
250.
250. It is here. You try to substitute here. X1 is 0. X2 is 25 inside here. 250. So this is the solution for the second round. But the next thing is we want to know whether this solution is the optimal solution or not. Whether this is the best solution. So what we are doing now, actually we are, where do I get it right now? Actually we are somewhere. Okay. I want to see the graph just now. Okay, never mind. Now we want to find Cj minus Zj value. We want to find the net evaluation index. How to find the net evaluation index? Cj minus Zj. Cj minus Zj. So what's the number here? 7 minus 5, 2. Here?
0.
0.
0.
0.
Minus
Negative 5
Minus
over 2.
negative 5 over 2. Now, to know whether this is optimal or not, all values of Cj minus Zj, that means all the net evaluation index must be negative, 0 or negative. That means less or equal to 0. To know whether it's optimal or not, the net evaluation index here, 2, 0, 0, 5, 2, all of this must be less or equal to 0. Does it qualify that conditions now?
Not yet.
No. Oh dear. So I have to do one more round. Go to step 1.
Yes.
We have to repeat. So in this case, we have to, that means this solution is not optimal. Not optimal. So for this one, all is not, it doesn't satisfy this condition. So not optimal. Not optimal, we have to do it again. So we have to find the net evaluation index that show the greatest value. What's the greatest value here?
2.
2.
2. Then where's the pivot column? This row, right?
X1. Yes.
X1.
X1. And then who will enter the basis after this?
X1.
X1. Now we do not know which one have to go. Let's find the ratio. I don't show you the thing. Let's find the ratio. Ratio is solution divided by pivot column coefficient. Solution divided by pivot column coefficients. Okay, let's put the ratio. 45 divided by 3 over 2. 90 divided by 3, 30. Here? 50.
50.
50. Which one to choose? Ratio?
30.
30.
30. Find the lowest ratio to determine the pivot row. 30. What's the pivot element? At the
3 over 2.
3 over 2. 3 over 2. So the next one, I wouldn't show the step by step. I just show the outcome. Okay, in this case, let's look what happened. What happened here? Here you look into this value, x2 equals to 25. Take note, x2 equal 25. Look at the graph. What happened is, just now we start at the origin. Now it moved to, it tests at this point, 25. 25 is still within the feasible area.
Yes.
It's still within the feasible area. But we do not know whether this is optimal or not using the this simplex method. So what we did, so we get at this point, we are testing this point now. It moved from here to here. The solution is x2 25, x1 is 0, z is 250. Okay, let's move on. This is the third solution. Just now, x1, s1 leave, x1 enter. So this is the third tableau. The third tableau. What's the value of x1?
30.
30. X2?
10.
10,
10. S1?
0,
0. S2?
0,
0.
The profit?
310,
310.
310. Okay, I repeat. Now the value of x1, S1 now become basic variable because it's in the basis. X1 is 30. X2 is now basic variable equal 10. S1 is not in the basis equal 0. It become non-basic. S1 become non-basic. S2 also become non-basic equal 0. And then the profit Z is written at the solution column 310. So what it says here in the graphical here, all okay, I forgot to ask. In this case, let's say we calculate, assume we already calculated the net evaluation index 0, 0, -4/3, -3/2. Is the solution optimal or not?
Yes.
Yes.
Yes. How do you know?
all 0 and negative.
All are 0 and negative, less or equal to 0. That means the net evaluation index are less or equal to 0. So the solution is optimal. Yahoo, right? Okay, what it says,
Finally.
what it says here graphically. Now we are moving to another point. Just now the first round we tested at this point. The second iteration we tested at this point. The third one we test at this point, and it turned out this is the optimal solution. Now, do we have to test any more point?
No need.
No need, because we already get the optimal solutions. Okay, we have a great day today. So this is the optimal solution. From the tableau, we can interpret x1 equals 30, x2 is 10, z maximum is 310. Okay, we are done. Any question? Brothers, sisters, any question?
So far, no question, Doctor.
No question. I hope
No
everybody,
question too.
I hope you understand this. This is the most exciting amongst the course content. Okay, if no question, shall we have Suratul As? If no question, then let's end our day with the recitation of Suratul As. Bismillahirrahmanirrahim.
Sorry, sir.
Yeah.
I just wanted to ask about the group assignment, sir. About the deadline. When is it due?
I would prefer the 2 weeks before, 1 week before last class.
All right. Thank you, sir.
1 week. I think I standardize everything 1 week before last class, but I still haven't get all the grouping yet. Still a few groups. Not even half have given me the group.
Yeah, so we are actually arranging the groups right now.
Okay. Okay. Any other questions?
No, sir. Thank you.
No. Okay. I think before I end the day, we wish you all Ramadan Kareem. I think tomorrow we are going to fast, right?
Tonight is Tarawih.
Tonight Tarawih. Okay, let's end our day with the recitation of Suratul Nas. Bismillahirrahmanirrahim. Thank you very much, brothers and sisters. See you next class.
Thank you so much.
Thank you, sir. Assalamualaikum.
Waalaikumsalam. Most welcome.
Thank you.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
You're most welcome. Ain. Okay, I end the meeting now. Assalamualaikum.